The second paper is on energy consumption and failure analysis of electro-pneumatic production system using machine-based simulation by Mr. Richard Gagné and Mr. Vivek Sharma from Famic Technologies. Uh, so, Mr. Richard is a professional Canadian engineer specialized in system design, fluid power, and simulation. He has more than 25 years of experience in project management and training in both academic and industrial settings in Canada and abroad. He has joined the Famic Technologies in 2005 and is the quality director of Famic Technologies. He obtained a bachelor degree in mechanical engineering from Laval University and a master's in engineering from École des Technologies Supérieures. Vivek Sharma, Mr. Sharma is a professional engineer specialized in system design, fluid power, and simulation. He has more than 12 years of experience in project management and training in both academic and industrial settings in India and abroad. He has joined Famic Technologies Pvt Limited in 2015 and is the operations manager of Famic Technologies Pvt Limited. He obtained a bachelor's degree in electrical engineering from Pune University and a master's degree in control systems engineering from COEP Technical University, Pune. I invite Mr. Richard and Mr. Vivek to present their work.
Thank you. So thank you very much for accepting our paper against this year. This paper was supposed to be presented by my colleague Pooja. He has been written by me, Pooja, and one other colleague in Canada, Elisa. Pooja could not be here today for personal reason. Okay, so last year I was presenting something about FMEA, automatic FMEA, and simulation. But I would like you to look at, as a software maker, we are not involved in parts. We are really a software maker since the last 40 years, next year. This is what we observed. Here are some facts that we observe since many years. Let's see, we are in system simulation. So most of our clients are OEM, manufacturer, system integrator. There is some fact and challenge in the industry. So for OEM, they like to improve their system accuracy. They think always about energy consumption, moreover today. And they want to reduce time to market. So reduce the system design time and optimize also the production time. Also, simulation is well known since I think, according to my study, the last 30 years we are talking about simulation. This is a great solution to avoid time and reduce time, avoid the time and cost of early prototyping. I mean by that, if you use, instead of creating a real prototype, you will be saving time for sure, specifically for system design. Also, simulation is a great tool to learn, understand the behavior. But if simulation is not used well, there is other challenge. So commissioning time, startup time can be lengthy. Sometimes, if the user is not well trained, they will use simulation and they will think the simulation can do everything for them. So they have to have a basic knowledge. Most of the time, I see also, since the last 20 years, there is a lot of simulation. Sometimes at OEM specifically, they do a specific simulation on this part, but it cannot be integrated in the system. So sometimes simulation are okay. So today I will present something pneumatic, a complete system. This is new for us, since the beginning of the year. There is 3 objectives. Taking advantage of a digital twin. Digital twin is another buzzword for me since the last 10 years with Industry 4.0. And why not trying to use this and examine the energy consumption. So this will be a bottle filling station, single bottle filling station, a work center that we reproduce as a digital twin. And also I would like to bring, once we have the system, we can do a redesign of the system thanks to the simulation. This is the objective of the project. Moreover, that's my idea. Since we have a FMEA capacity, let's introduce some degradation in the system and see what will be the impact on the cost of the production or the energy consumption. So can you start the video, please? I will describe. So this is a full system integration, multi-technology system. We have, some of you will recognize, this is a Unity platform. This is a bottle filling station with 4 steps. So we implement the real system, based on the real system. This is a work center. And hereby, I'm from Canada, we put maple syrup. This is a maple syrup bottle. And the system is really driven by the simulation engine, a multi-technology simulation engine. What else? In Unity, we can program sensor. Each object is independent. So it acts similarly as a real system. You have the pneumatic system for function. We have the HMI to count. And thanks to, again, our controller in the system, we reuse it to calculate the energy consumption. Both conveyor and compressor are driven by an electrical. We have VFD. And this is controlled by a PLC. And then you will see the logic behind in SFC, complex SFC, that drives the entire system in real time, based on the sensor in there. So this is the idea of the project. I will let Vivek, my colleague Vivek, to present the detail.
Okay, thank you, Richard. So if you see here, we have 4 technologies which are driving this plant right now. All of them are integrated into one software. We can close the video, please. Okay, so we saw the 4 technologies integrated together. Now let us see the individual technologies and what goes behind in their operation. So this is the pneumatic plant. You will see this is pretty easy to understand. We have kept a compressor here to pump the air through a FRL unit. We are using the solenoid control direction control valves, which are in turn controlling the operation of each cylinder. We have 4 operations taking place in the plant right now. First one is the reject bottle, the bottle filling, cap loader, and bottle capping. Please note that the components being used in this system are the actual manufacturer component data. For now, we are using them from Aventix, Genetics, and AMN Organ. So I was talking about the components which we are using. This is possible because we have the provision to model them in a hybrid mode. So what do I mean by that hybrid mode? You will see we have, of course, taking the basic equations which are controlling the performance of any component. Plus, on top of that, you are able to input the performance curves, which are the actual parameter which are obtained from the different manufacturers. All of them will integrate together to give you the output of the component performance. This is an example of a compressor which we are seeing right now. Similarly, you can see we have the pressure relief valve, we have the cylinder parameters, and we have the direction control valve as well. This is the electrical system which is mainly driving those 2 motors, which are in turn controlling. So we are using 2 different asynchronous motors. One motor is basically controlling the conveyor on which the bottle is moving, And the second motor is controlling the compressor RPM. Okay? So you will see we are using the VFDs, they are from ABB, and we are varying the parameters of VFD in turn to control the RPM of the motor and thus the flow output from the compressor. These are the parameters which are being used for this experiment. Now, this is the automation and control system. So basically, we have input. We are taking the input from different sensors which have been put over the cylinders in the pneumatic system. The signals from the pneumatic system cylinders, the sensors, they are coming back here. They are being, through different logics, they are being controlling the output of the solenoid control valves which we saw in the pneumatic system. On the right side, you see this is a virtual HMI panel. This represents very closely to the control blocks which are easily found in the different plant. You will see it constitutes of all the required which you need to monitor your plant and productivity, along with the lighting, LEDs. It has the push buttons, switches, emergency stop, plus a display as well, which will show you the number of count of bottle which have been successfully filled, or if something has been rejected, that can also be displayed over here. Okay, so we are trying to monitor the energy and air consumption of this plant by varying the different parameters inside the components being used in the pneumatic system and the electrical system as well. So we are using these equations to get to the energy calculation. Total energy is nothing but integration of power over a period of time. Average energy consumption is the total energy per relative simulation time. And we are calculating the total cost by total energy used into electricity price. For this study, we have taken $0.3 per kilowatt hour as a sample cost to calculate the total cost being involved. Similarly, the average compressed air consumption is integration of flow with respect to the relative simulation time. Okay, so these are some of the findings which we have found in our experiment. Please note all these findings which we are running is based on the 25 cycles iteration. So that means once 25 bottles of maple syrup has been filled, we start and stop the simulation again for the next parameter readings. Okay, so in the scenario 1, you will see this is the by default parameters which we have kept there: the compressor displacement, accumulator volume, pressure relief valve, pressure reducing valve setting, and the angular speed of the motor. And with this parameter, you can see the total cost which we arrived is at around $18. Now in the next iteration, what we did, we reduced the compressor displacement. Okay. Now you will see if you go from 200 to 100, there is a very, very effective reduction in the total cost. It brings it down to 9.8. The next process, the next scenario, what we simulated is, now we change the accumulator volume. So we bring it, eventually we bring down the accumulator volume to half, from 40 to 20. If you see in scenario 4, we are further reducing the total cost involved to 6.15. The next iteration we run is now reducing the FRL pressure setting, the pressure reducing valve. And if we bring it down, again you will see in the scenario 5, we are there is a slight change in the total cost involved. And finally, in the scenario 7, you will see we are also reducing the angular speed of the motor. And finally, we are able to go to a 3.85. It's a big considerable difference in the total cost involved in the plant operation. Why we did this basically is we did not at a time varied all the parameters. We did that one at a time. The reason being, we wanted to see what is the impact of each component parameter with respect to the total cost involved in the plant operation. This is the next level of study which we incorporated in this experiment, which is the failure mode and effect analysis. My colleague Richard presented a paper on this subject in the last year conference here. So I'll just give you a very brief of what we are doing here right now. Through Automation Studio, it gives us a capability that we can introduce the faults inside each component, whichever we want in the system, and we can see the progressive failures which it generates in the plant. So for this study, what we did is, for the filler cylinders, we introduced some faults inside them, and we want to see what is its impact on the total cost and the compressed air consumption. Okay, so as I mentioned, one more thing is we are not introducing any hard faults, as in the cylinder is jammed or the port is blocked, because eventually it will stop the production of the plant. It's of no value for us to study. So we are putting the failures which actually the plant is running, but it is impacting the behavior and the interaction of all the system together, and finally on the output, that is the total cost and the consumption of compressed air. So if you see, if there is no faulty component, if you see the scenario 1, there is no faulty component, we found the average compressed air consumption to be around 100 standard liters per minute. The next thing we did is, in the filler cylinder, we introduced some internal leak. The value is at 5 liters per minute per bar, and you will see there is an increase in the consumption of compressed air to 116. In the next scenario, on top of internal leak, we also added an external leak, which is valued at 20 liters per minute per bar. And when we did that, you see we are almost increasing the compressed air consumption by 50% to 150 standard liters per minute. So this is just one scenario which we are able to simulate. This is an ongoing study. We can introduce multiple faults in multiple components being used in any system, and thus we see what is its impact on the performance. So in the failure mode and effect analysis, it is able to generate a report at the end, and for each failure, it will give you what are the probable causes of those failure. So if something like that happens, it's very easy to identify this is the cause and this is the effect which is happening on the output or the production of the plant. And finally, for conclusion, I will let my colleague Richard to wrap it up.
You could do it as well.
That's okay.
Okay, so I come back on my first fact. So simulation has proved once again that this is a wonderful tool. You can do what-if scenario, whatever you want. The virtual environment, which is the digital twin, you have an existing design or an existing machine. You replicate it virtually. You can do the change of component parameter. It allows to really to identify the key design improvement. Third point, same virtual environment allow us to now, with simulation, to do degradation and see what if again. But our case study is at the first step. So we will do more with the same project. We want to experiment more. Next step, for example, we can use OPC server link to the real machine. This is another example. We can change the production type. If we change the liquid, there will be an impact. We would like to do a longer cycle when we do progressive degradation. Carrying out these experiments with a physical prototype could be proved difficult. That was my first point. So this is a presentation that we wanted to present you here. Thank you very much.
Thank you.
Thank you so much for your work. It was a nice analytical study. I have just one to two queries. Basically, you have performed your analytical study on Automation Studio, right?
Yes.
So that the study has not been validated experimentally. So what are the assumptions that you have taken for your analytical study? I mean, because there may be certain frictional losses and all those things. So how you have characterized those losses and all those things?
Yes. So I will answer your two-part question. First is, of course, we are not doing it in a real prototype, but as I mentioned in starting, we already created the digital twins of different manufacturers. Usually we get an accuracy of around 95% for those. So even though they are not on plant, but these studies are using the actual performance curves and the parameters which are being built by the different component manufacturers. Okay. With respect to the other parameters, which you mentioned, the friction and others, you are right. At this point of time, we are keeping some default values in all the, let us say, the cylinders, the damping coefficients and everything are certain default value which we have taken. We have not experimented with those values yet. Right now, we are focusing on the faults, which I have told you are the two faults in only the internal leak and the external leak. What you are saying right now is, of course, the next phase of study. We will try to introduce more faults, maybe increase the friction, the damping coefficient, and then we will see its effect on the overall behavior.
Okay, and my last question is, you have worked on the system, high electro-pneumatic production systems. So during your analytical study, have you identified the particular component, those who were the major contributors to the energy losses?
Yes. First thing is, of course...
Let's get back maybe on the last page. This one.
No, I think this, yes. Of course, if you see the major impact which occurred is with respect to the compressor displacement. Now, let me please tell you this. We are aware that if we reduce the compressor displacement, we reduce the pressure values, we reduce the angular speed, it affects the production time. We are aware of that. But when we do more experimentation through different iterations, we found that the time loss is really negligible with respect to the benefits it will give you if you really reduce these parameters and reduce your total cost.
Okay. Is there any questions from the audience? So I think there is not any question. So thank you for your presentation.
Thank you.
Yeah,
Thank you very much. Can I ask Mr. Vineet Taneja to hand over the memento to the speakers?